So, let me continue with the slope stability, the other aspects. We have considered so far only for the granular soil, that means where there is only one component, shear component is that there is friction, and there can be only cohesion, there can be both C and cohesion and friction. So, I will take next the thing. Let me see this one, the soils with two component. So, we can see the contemporary methods of investigation based on assuming the slip surface and a center about which it rotates. That means, slope stability when the granular soil we have considered a planar slope. So, if it is a slope here like this, the failure plane also parallel to this at some depth, somewhere there the failure plane is considered there. But when there is a soils possessing cohesion and friction, then there will be not planar, it will be it is something like this shown here. So, the equilibrium. So, that means to do the analysis, assume a slip surface and a center about which is rotated. That means, we are assume one slip and also we assume the point about which it is rotated, the center of the slip, and studying the equilibrium of the forces acting on this surface and repeating the process until the worst slip surface is found. That means, I consider a slip surface, and based on this slip surface whatever resistance is there and whatever disturbing force is there, the ratio based on that I will find out factor of safety. Similarly, I will consider another center here, another failure, something like this, and based on that again I will find out the factor of safety. Like that, we used to assume a different trial slip surface with different center and do investigation and find out the slip surface for which we are getting minimum factor of safety. That is the conventional way of doing slope stability analysis, and the procedure will be repeated until unless we get the critical slip surface. The worst slip surface is that surface which yields the lowest factor. That means, we do analysis, while doing analysis and different factor of safety we are getting, that means, the slip surface will be the critical when the factor of safety become minimum. F is the factor of safety, and the factor of safety is the ratio of restoring moment to the disturbing moment. Restoring moment is what actually, because of this, when there is a this soil mass is trying to move, this is the disturbing, it will try to move this way, and restoring moment is what, along this failure surface there will be some shear strength will develop. That shear strength, if I take moment with respect to this, that is becoming restoring, that it will resist the movement of this mass. So, these two we have to equate, and obviously, resistance has to be always more than the disturbance, then only it will be stable. So, with this factor of safety again once again defined. So, now I will go these are the procedure generally follow. You can see here initially this slope failure surface is starting from the toe and passing through this one slope considered, then this is the center, and you may do analysis. Another sloping slip surface is this with this center, you do the analysis. Like that, infinite number of failure slip surface can be assumed and analyzed, and finally, we have to find out a sufficiently large number of factor of safety with sufficiently large number of slip surface, and finally, we examine which one is giving you the lowest factor of safety, and that corresponding to that factor of safety corresponding slip surface will be the critical slip surface, and based on that finally, we do the final factor of safety analysis. So, this is the way generally we follow, and this is you can say typically suppose final slip surface is something like this, and this is the slope, and there is a slope angle, and this is the slip surface, and then this slip surface will have a length, certain length equal to L, and this length will be approximately, if I consider this as a circular arc, portion of a circular arc, then length will be r into theta subtended here, r multiplied by theta will be the length here, curve that circular arc length. and along this, based on the shear strength parameter, the shearing resistance will develop, and assuming the point of assuming this slip surface is what is the meaning actually, that we assume that this mass, soil mass, from here to here, this soil mass as a block will try to move along towards this. So, when this try to move, that means it will rotate, since it is a slope and we have assumed a circular slip surface, that means it will rotate, this mass will rotate and it will rotate with respect to some point, that is center. So, if this is the center, that means the center of the entire mass is suppose somewhere here passing through this, then that means how much eccentricity it has. So, this eccentricity, suppose if I draw a vertical line, and if you draw a vertical line, this distance become the eccentricity of the mass. So, that means this weight multiplied by this distance, that is the moment which is causing the disturbance or causing this mass to move away from this toe, whereas along this length of the slip surface, whatever resistance is developed, that resistance multiplied by this radius will become the another moment which will be restoring, that means counteract this rotation. So, that to be estimated. So, once you estimate both, then we can find out the factor of safety. So, we go to the next slide. You can see here so this analysis intended to give the stability of an embankment immediately after its construction. That means, what actually we are trying to introduce here undrained condition, that means embankment immediately after its construction, that means there is no time to dissipate the pore water pressure. At this stage, it is assumed that the soil in the embankment has no time to drain, and the strength parameter used in the analysis are the ones representing the undrained strength of the soil. Undrained condition we do, that means quick test CU, based on the CU. So, that CU can be either from UCC or from undrained triaxial test. Based on that, whatever parameter we do, and based on that parameter, immediately after construction there will be some condition, and after some time sufficiently after the construction, the condition will change actually. So, so immediately after construction, when you do the analysis, you do the undrained parameter, and if I consider the undrained parameter, based on that, whatever failure trial slip surface I have shown and mass with eccentricity I have shown, then what is the disturbing moment and what is the restoring moment, based on this undrained condition I can find out now. Considering the figure, the sector of soil cut off by an arc AB of radius r. So, that is the thing I have shown previous one. Let W equal the weight of the sector and G is the position of its center of gravity. As undrained condition is considered, the shear strength component is Cu. That means, if I go back to your previous one, that means along this Cu is there and W is acting here. Okay. So, if I do that, then you can see taking moment about O, the center of rotation center of rotation, that means I have taken a slope something like this. Okay. So, if this is the slope, and then moment will be W into multiplied by E, W multiplied by E. So, I think we can write beta W multiplied by E, then it will be, you can see that must be equal to Cu theta multiplied by r is the arc length multiplied by Cu, theta r multiplied by Cu is the force. That means, this is actually theta multiplied by r, this length L equal to theta r, and then force equal to your theta r multiplied by Cu, and moment will be equal to theta r Cu multiplied by, again this force is how far actually at a distance r. So, you once you multiply. So, that is why Cu multiplied by r multiplied by theta multiplied. So, this is length, this is lever arm, this is the cohesion. So, ultimately this becomes Cu r square theta. Okay. So, this force becomes Cu r square. So, this force, if I take moment with respect to the Cu r square theta. And for equilibrium, you can see restoring moment and disturbing moment. So, this part should be bigger, this part should be bigger. So, Cu r square theta, that is actually restoring part which is developed from the soil itself, and this is actually externally because of the soil weight it is causing. So, this divided by this is a factor of safety. If I want this is equal to 1.5 or 2, then we can find out the other required things. So, theta and other things if it is required, or generally we do not do this way, we do we assume different slip surface like this, and we will do the slip surface, and then you find out what is the factor of safety because of based on this calculation. If I take another failure slip surface something like that, then again I will do W 2 E 2, and then again I calculate this, then I will get F 2 like that, F 1, F 2, F 3 like the n number of F I will get, and from there I will find out where F minimum, and F minimum gives you the critical slip surface, that we can find out. Now, while doing this, one thing to be remembered, that as when there is a clay soil, if the slope made of clay, then sometime the cracks forms. At up to what depth actually cracks can go, that we have discussed during the earth pressure, and we have shown when there is a pure cohesive soil, that depth of tension crack will be equal to 2 Cu by gamma, and in fact, depth of unsupported cut it will be just double, because the pressure diagram was something like this. Okay. Pressure diagram was something like this. This is actually 0 tension, and here is the maximum tension. This is a depth of 0. That means, tension crack can reach up to this, and this depth is called Hc. And since this is a negative pressure and this is a positive pressure, so that means up to this much if I go, where actually total force area of this diagram when become equal. So, that much up to that much depth actually wall is not getting any additional pressure. So, because of that, double the depth of tension crack we can excavate without support. So, that is a different thing we have discussed already, but now as I have mentioned that if the slope is made of clay, in that case there is a chance of tension crack. So, if there is a tension crack start from here, and if I assume a failure plane something like this passing through this, then beyond that actually I will not, though the slip surface may go here, but I cannot consider up to this, I have to stop here. So, I have to consider slip surface up to this. So, that modification you have to do while calculating the length of the arc, which is equal to theta into multiplied by r, and because of this tension crack this I have to stop, then r will change, and accordingly your length of arc will be changing, and if the length of the arc change, then accordingly this portion also will be changed. So, if there is a tension crack, your resistance is getting reduced. So, that to be considered also in the analysis. And you can see here once again it is shown the tension cracked here, and we assumed a failure plane something like this, and it is supposed to go up to this, but because of this tension crack I have to terminate here. So, beyond that the slip surface will not have any resistance, because before that it gets separated, then because of tension crack. So, I have to consider only this, which will be original theta was suppose based on this was theta, but I have to consider now theta dash. Based on that I have to find out L equal to r theta dash, and r theta dash multiplied by cu become the force, and multiplied by r equal to moment, and that moment to be used to calculate the factor of safety. So, here the effect of the tension crack is to be shorten the arc AB. So, this arc AB, this is A and B, this original was this AB and now it is AB dash. If the crack is to be allowed for the subtended angle to be reduced, that means original angle was this, now the modified angle is this, that to be taken. But full weight of the sector to be, but while considering the weight you have to take entire weight, but that weight also create weight on this. Then so, this is the one to be considered. Next one, so this is the example, actually one simple example we have given here. This is not drawn properly, of course, this could have been little sorry. You can see here the figure gives details of an embankment made of cohesive soil with phi equal to 0, that means no friction, C equal to 20 kilonewton per meter square. The unit of the soil is 19. For the trial circle shown, determine the factor of safety against sliding. That means, this is in this part to be ignored. Initially, suppose this trial surface was something circular, actually it should be circular, it is not, does not look like circular. If it is like that, and then for the trial circle shown, determine the factor of safety against sliding, and the weight of the sliding sector is 346. Suppose this under this it was 346 kilonewton, acting at an eccentricity of 5 meter from the center. Center is here and it is acting here. So, this distance is 5 meter. What would be the factor of safety? The weight of the sliding factor is 340 acting at an eccentricity of 5 meter from the center of the rotation. So, so for the trial circle shown, determine the factor of safety. So, initially because of this, what would be the factor of safety? Okay. And what would be the factor of safety if this I is missing, the shaded portion of the embankment were removed? That means, this is the way sometimes we solve the problem in the field, when at a particular slope looks like unstable, then if we remove some amount of soil from the top, then it helps, actually it makes stable. So, second part, so in this first part actually you will find out what is the factor of safety, and then second part is shown, if this much soil is removed from the top, what will be the reduction in factor of safety or improvement in the factor of safety. So, we will go that part next. And so disturbing moment will be disturbing moment will be 346 the W and eccentricity is 5. So, it become 1730 kilonewton meter, and restraining moment will be equal to as we have given C u r square multiplied by theta. So, all those things are given. So, C u is 20, r is 9 meters and theta actually given 70 degrees. So, if I convert in radian, you have to multiply by pi by 80. So, this is the one. So, it gets the value 1918 kilonewton meter. So, F become your F become 1980 is a restoring and disturbing is 1730. So, your factor of safety become 1.14, quite close to 1 only. So, and now you can see second part, area of the portion removed, you can see area, approximate area is 1.5 into 3 area removed will be 4.5 meter square, and then W removed, weight removed, will be 4.5, and you take 1 unit weight multiplied by unit weight of this soil equal to this. So, 4.5 into 1 is the volume and multiplied by unit weight, this that gives you 85.5 kilonewton, and eccentricity, that eccentricity of that mass will be equal to 3 point, approximately you can find out 3.3 plus 3.3 plus 1.5 by 2, this is actually 5.7 meter. So, that means, when there is a slope here and like this, and we have removed this amount of soil, and this is 3 meter and this is 3 meter, and there is slope also mentioned here, what is the slope. So, we can find out where it is acting. So, that point actually is shown by 3 point, up to this is 3.3 meter plus this distance. So, this will be approximately this plus this divided by 2. So, 5.7 meter. So, relief of disturbing moment, relief of disturbing moment will be equal to 85.5 W and it is 5.7. So, that become your 490 kilonewton meter. So, now new factor of safety will become 1980 is the resisting unchanged, but disturbing moment is reduced, originally was 1730, now 490 is minus. So, this gives you factor of safety equal to 1.6. You can see that originally your factor of safety was 1.14. When you remove some portion from the top, if you remove from the bottom, the effect will not be that much, it will be negligible, but when you remove from the top, the effect will be maximum. So, you can see that improvement of factor of safety. So, this is the practical solution we adopt in field. When there is a slope, we find that it can be unstable any time. So, in that, to make the slope stable, we can cut from the top actually some portion, or sometime if we have a steep slope, instead of making a simple slope, we can make a benching, that means, this is the one. So, we can do small benching. So, we can do small benching. So, then so if I consider from here to here quite steep, but when you go by this looks like steep, but if I go this way this will be quite a mild slope. So, that is the concept sometime adopt in the field to make to have the better factor of safety. You can remove some portion from the top of the slope. And so, this is the problem which is explained already. So, let me see the next one. With the partially saturated soils, that means, when the soil is partially saturated, when it is not saturated in fact, then when you do triaxial test, you test your failure envelope will be parallel, and when you have the partially saturated soil, then your failure envelope will be something like this. That means, soil will possess both C and phi, and if it happens so, in that case you can see both C and phi will be there. So, the total stress analysis can be adopted to cover this case by assuming a slip circle procedure and dividing the sector into suitable number of vertical slices. The stability of one such slice being considered in the figure in the next slide will show, and at the base of the slice set up its weight to some scale, draw the direction of its normal component n and component triangle forces, determine its magnitude together with the magnitude of the tangential component. That means, so total stress analysis will do when there is a slope something like this and this, I can make number of slice like this, and this slice will have suppose a failure plane is something like this. So, this is the slice. On this slice I will find out the weight, and I will have a normal component, I will have a tangential component, and I will have a gravity load. So, based on that, so graphically we can find out for each slice, and finally, I can find out number of slice if I do this way, and by summing all those forces in the same direction, I can get total tangential force or total normal force, and based on that I can finally do the calculation whatever we have shown in the previously. So, let us look at the next page, then it will be clear. You can see suppose the soil possessing C and phi, and in that case the entire this slip surface suppose is critical or may not be critical. This is one of the assumed trial slip surface, and for the analysis purpose we can divide a number of slip, and for each slip I can find out normal and tangent, and how to do that. So, I can isolate this one, assume this equal to this, actually otherwise this problem cannot be solved or it can be ignored, and then the W can be calculated in scale, and you can draw parallel to tangential to this and to this, and then draw normal to this, then I will get the force polygon for this particular slice. So, each slice, so instead of isolating at the midpoint I can do this, and from there I can find out T and N. I can find out the effect of tension crack. If I take, then again I have to subtract HC. Suppose if it is tension crack is coming here, then it will be terminated here, terminated here, and I have to take this angle. So, that is similar way, but slice will be started from here, you have to ignore this. So, by this way if I do, then you will have calculation will be, you can see here the taking moment about the center of rotation O. So, number of so suppose this is the failure plane. So, we will have this. So, like that each point we will have like this. So, T and N. So, R multiplied. So, it is at a distance r. So, center is here. So, this T is this one, r multiplied by T, r multiplied for each, r multiplied by T, T I will find out for each, and then if I sum it up, that you will get a total resistance. So, disturbing moment I will get, restraint moment will be you can say r and C r theta plus n tan phi. So, this is the one multiplied by r, that will be restraining moment, and then ultimately your equation become C r theta plus sigma n tan phi by sigma t. So, that means whatever different slice I make, I have to find out n at different point, n I have to find. So, I have to sum it up, and I have to find out the t at different point, and then finally I sum it up, and then I use this equation where the soil possessing both C and phi, and then based on this calculation I can find out the factor safety F. So, I hope this is clear. So, when there is a slope like this, let me once again I will do, if there is a slope, suppose something like this and this, and your failure surface is something like this, and then center is somewhere here, and then if I consider a slice from here. So, its gravity will work like that, tangential will be work there, and then normal will be acting like. So, I will find out graphically by reading the n and t. So, for similarly for each slice I find out t and n. There is another. So, here also I will find out t and n. So, all t, if they are in same direction, simply I will sum it to get the total t, and sometime while the change of this one, some t will be in this direction, some t will be in this direction. So, if I consider this direction is positive, if it comes the other direction, I will subtract it. So, that way, so this is the cumulative t, and this is cumulative n will be all positive. So, in normal direction. So, if I know the value of c, value of r and theta and n from each slice and t from each slice, then I will do this calculation to get the final value of factor of safety. So, this is when soil is not saturated, that means when partially saturated, when soil possesses both C and phi, then this is the analysis to be done for finding out factor of safety. Okay. So, I will again some more thing I will take in the next module. Thank you.